Okay, welcome to the video for 1.5 notes. This is about inverses. And by the end of this, you'll be able to find and verify inverses of functions and relations. So first off, what is an inverse? This is a reflection of a function over y equals x. So I've already drawn in these little lines here for y equals x in the first two. And we're going to reflect these over y equals x. You also need to know numerically, if the point AB is on the function, then the point BA is on the inverse. And then you need to know what is a one-to-one function. And a one-to-one function is a function whose inverse is also a function. So it passes the vertical and the horizontal line test. So if we look at these, actually let's just hop into these. We want to know, determine if the graph below are functions, if the inverses will be functions, or if the graph is one-to-one. So for this first one, does it pass the vertical line test? Well, it does. So f of x is a function. Does it also pass the horizontal line test? It does. There's no horizontal line that I can draw through here that would hit the functions twice. Therefore, f inverse x is also a function. So the way we write that is f inverse x is a function. So if you think back to -1 exponent, that always put the base in the denominator. So we're creating inverses by raising something to a power of -1. But all you need to know is this is f inverse x. And let's actually put it up here. So f -1 is the notation, and that means f inverse of x. There we go. Okay, so if we're to flip this guy over, it's going to look a lot the same. I don't know that I don't know if I'm going to be able to draw it perfectly, but basically if I flip that over, it's still going to look like this. This point ends up over there. This point ends up over there. So we're flipping the x and y coordinates as written above here. So if we want to do it manually and flip every dot, or change every point, we would flip the x and y's. But it looks something like that. All right, so how about this one? Well, already it's not passing the vertical line test. So f of x is not a function. Okay, and then as far as the horizontal line test, it does pass that. So f inverse x is a function. Okay, if we were to flip this over, we would end up with something that looks kind of like this. So it is a function. Pause the video here and see if you can come up with these two answers here as far as not a function or whether it's a function or not for f of x and whether it's a function or not for f inverse of x. And then when you're ready, unpause the video and see the answers, and we'll talk about one-to-one. Okay, so hopefully you came up with these, but f of x is a function and f inverse of x is a function in this case. And if we were to flip this over y equals x, it would look something like this. And so we can see it passes the vertical line test even when it's flipped, right? But we can tell that back before it's flipped, so I'm going to erase this just to take a look at this graph here. But we can tell that it's not going to pass the it is going to pass the vertical line test and the horizontal line test, which means that when you flip it, it's still going to be a function. Now, what does that mean for one-to-one? Well, when they're both functions, then it is a one-to-one graph. So let's go back and write one-to-one on the ones that are. So one-to-one on this one, because it's a function in both situations. In this case, it is not a function when the original function is not a function. F inverse of x is a function, so this is not one-to-one. And then this one would be one-to-one. And then this last one definitely is not a function. It does not pass the vertical line test and the horizontal line test. It does not pass either, so it is not a function in either case, so not one-to-one. Okay, now let's get into actually finding the inverse. So we're going to replace the f of x with a y. So this is very step by step, and then you just have to do some algebraic manipulation here. So I'm going to make this y. The rest of this stays the same. And you can combine these first two steps once you get used to it. But now we're going to switch all the x's to y's and all the y's to x. So this would become x equals 4y minus 12. And now we're going to solve. So now I have x plus 12 equals 4y. That is an equal sign there. And then I divide by 4, and just make sure that you divide everything on that side by 4. So you should end up with either you keep this all together or you have to divide it into each part. So you can have x over 4 plus 3 equals y, or this could also be x plus 3 over 4 equals y. But I want to make sure that you know if you simplify it, you should be dividing it into both parts. Okay, a couple things you need to know about the domain and range when we're talking about inverse. So the domain of the inverse is the range of the original function and vice versa. Okay, so we're going to find the inverse here, and then we're going to see how they're just the domain and range switch on these. So the inverse can be used to find the range of the original function algebraically. Before, we only knew how to find that graphically, but now I'm going to show you that you can, in some cases, find the range of the original function algebraically just by finding the inverse. All right, so our first step here was to replace the f of x with y and then switch all the x's and the y's. Like I said earlier, you can switch them right away. And hopefully you think of f of x as y pretty intuitively. So that makes us just a little bit faster. So right away, I'm going to make this f of x, x, right? It is y, but I'm just going to go ahead and make it x. And then all my x's are going to become y's. Okay, so a lot of times, and we do this problem fairly often in class, but I see kids get stuck on this and they're not sure where to go. So really, there's not a whole lot of things you can do with this problem right away, except multiply by y plus 1. So I would just go ahead and do that. So x times y plus 1 is on this side. Whoops, there's my 1. And then on this side, when I multiply, we'll just write it out, y plus 1. So we know where that's coming from. When you look back at your notes, these are going to cancel out to 1. 1 times y is y. Okay, so my goal is to get the y's on one side and the x's on the other. That's not going to happen at this point. So at this point, go ahead and distribute here. Okay, now, oops, that's supposed to be an x there. Now let's move this to the other side. And with these types of problems, and we'll get into proofs where you just have to try something. Just go for it, see if you get there, and if you don't, try something else. This is going to work because I've done this problem before. But in the future, when you're unsure what to do, try something and just see what happens. Okay, so I'm going to subtract xy. These cancel out. I'm left with x equals y minus xy. And I'm getting closer because now I'm going to factor out a y here. So once I factor out that y, I can get rid of what's next to it and isolate it. So I just need to divide by 1 minus x, and I'll end up with, I'm going to run out of space here. So y, when I divide this, I have x over 1 minus x. Now I have all my x's on one side and my y by itself. Let's take a quick look at what that looks like graphically. So here's my original function. Here is y equals x. Right there. And so when I graph what I found as my inverse, it should look like it's flipped over. And it is. Now I want to look at that domain and range. Okay, so let's go back and find it algebraically and confirm it graphically. But my domain of this function, well, I could not have negative 1 in here. So we go from negative infinity to negative 1, hop over negative 1 to infinity. Okay. We're going to skip the range for now because we do not have a way to find that algebraically. But if we look at the domain of now this function, this is our inverse. So let's actually write this with the correct notation. So we know that we found the inverse here. So 1 minus x, this is our final answer for the inverse. Okay, so for this one, what can we not have in here? Well, we can't have a 1 in there. So this has changed. This was a negative 1. But now it's going to hop over 1 and go to infinity. Okay, so that will help us find our range. This domain is the range of our original function. And I'm just going to go ahead and write it in here. So negative infinity, 1, 1, to infinity. Okay, so what I should be seeing in my graph is when I'm looking at the domain, so looking at it this way, going across horizontally, I'm skipping over -1. And when I'm going up it vertically, I'm skipping over 1. So let's go back and take a look at that. All right, so I'm even going to put in a line there so we can see it. -1, I am definitely skipping over -1 there. And then I should be skipping over, as I move vertically through my graph, I should be skipping over 1. And I'm definitely skipping over 1. So that looks just the way we expected. And you can see how we were able to find the range by using the domain of the inverse. Well, this is also true for the range of the inverse. So we can just copy this one down here, and then we'll quickly look at the graph of it. But I would have negative infinity to -1, hopping over -1, and going to infinity. I'm going to move this over so we can see it better. But let's put our inverse in there. So the domain of our inverse says hop over 1. Well, there we go. There is 1. And then the range is saying hop over -1. So where is -1? Well, that is being hopped over for our range. All right, so let's try some other problems here. For this one, I'd like you to go ahead and try it. Pause the video, see if you can come up with it. I will get you started here, but this f of x needs to become y, or we'll do it the long way really quick. So this is like this, and now I'm going to switch the x and y's. So my x is over here. This becomes y cubed minus 4. Now I'm going to pause, and I'd like you to solve for y, do it all, and then check your work and see if you came up with the same thing as I did. Okay, so look through my work and see that you came up with the same thing, but I added 4, and then I took the cubed root, and then I put it in my function notation. So f inverse x gives me the cubed root of x plus 4. All right, so right here, what is the domain and range of this? So the domain is all real numbers. We have no restrictions on here. We do not have any square or even roots, and we do not have any x's in the denominator. So it is all real numbers. Now the domain of my inverse, well, we do have a radical, but if you think back, you can have an odd root, right? An odd root, or sorry, you can have any number under an odd root because you can have negatives under an odd root. So this domain is actually infinity. So this domain tells us what this range is. So that's infinity. And this domain tells us what that range is. Okay, looking at those graphs, there's my x cubed minus 4 down here. There is a line I want to flip it over. And you can see that the domain and the range are all real numbers. They're going to extend to infinity in both directions. And when I put in the inverse, well, there it is. I still have a domain and range of all real numbers. All right, let's try this last one here. And this one has a little trick to it as far as finding the domain and range. So go ahead, pause your video, and do this from the beginning to the end and see if you can come up with the inverse function, and then rejoin me when you're ready. Okay, so I took out my f of x, put in a y, then I switched my x's and y's. The first step here was to square both sides. I'm actually going to show that in here. So I squared this, which made it so I squared this, brought it down. This became y minus 5. And then we add 5. And now we have our inverse. So the f inverse of x is x squared plus 5. All right, so now this domain and range flippability is pretty important. So on this first one, we cannot have a negative inside of here for an even root. So this ends up to be, we can have a 0, so it's 5 to infinity. And then we'll come back to the range here. So what do you believe the domain of this to be? Well, looking at this, there's no restriction. So you would be thinking that it's all real numbers, but actually it's not. And so while in these cases before, it was helpful to find the inverse to find the range of the original. Remember, we found the inverse, found this domain, that told us this range. These work hand in hand, but it's not very helpful to find this. You actually need to know what the range is because you need to know what this function looks like just inside your head to figure out what this domain is. Okay, so if we think about the domain of this, well, let's graph it. Graph it in our notes because I think it's useful to have right here instead of looking at Desmos. So the domain of this, well, this is actually the function that starts at 5 here. Right? So that's our domain. That means our range going from negative infinity up, well, it just starts at 0, including 0. We don't have any values below 0, and it does go to infinity. For all even roots, that is true. So then the domain, well, if I were to graph, I'm going to change my colors here. This right here, x squared plus 5, well, it starts up here at 5, and we know it to look like this. But when we're talking about an inverse function, this is true, this is the inverse, but only for x is greater than or equal to 0, right? So what that means is when I come over here, only the part of the only part of this function that is actually the inverse of this function is this much. Right? And that's what we're looking for here. We're looking for the actual inverse. So it's only that part that's being flipped over. So you need to know that. You need to know that about the graph. And then you would need to state that as part of your inverse. Okay, so the domain then of this, we're starting at 0 and going to infinity. And the range starts at 5 and goes to infinity. Okay, so we'll practice this some more so that way you understand it. Let's go over and start verifying inverses. Okay, so now we're going to verify, and graphically is easy. We're going to draw it on here, but you can also do it on Graphing Calculator. But go back to example 3b and graph both f of x and f inverse of x, and I seem to be missing a negative sign there, so add that in. I wrote them down over here, so that way you don't have to flip over. Okay, so I've gone ahead and graphed this, and then you can do this on a graphing calculator, but let's go ahead and get this on a piece of paper to look at and use these anchor points. So pause and actually write down these anchor points that I found. But I just found them because I know that this is just x cubed being moved down 4, okay? And then I also know how to graph this by moving this over to the left, but we could also just take these points and flip them, flip the x and y, and that's what I want to actually look at here. So on the previous page, I had said that if you have a function where a and b is on the function, then when we go to the inverse, so f of x, f inverse of x, then we should have ba. Right, so let's take a look and see if that happened. That would help us graph it. Or if we graphed in our graphing calculator and we want to check it, because sometimes it's hard to tell when we have a complicated graph, we would just want to look at some points. So let's list some points that we have here for x and y. I'll do it over to this side. So x, y, well, we have the point -1, -5. We also have the point 0, -4. We have the point 1, -3. And we have the point 2, 4. Okay, so I'm looking to see if the following points are on my inverse, right? So that would mean that I should also have -5, -1, -4, 0, -3, 1, and 4, 2. I just flipped all of these. I took all of these and just flipped the x and y. So now let's see, -5, 1, -1 is there. -4, 0 is right there. -3, 1 is right there, so that works, and 4, 2. So I have verified that this is an inverse, so that's great. All right, inverse composition rule. This says that, let me write this out. Okay, this big long statement, copy it down, and then let's talk about it. So pause it, get it down, and then we'll talk about it. All right, so this is saying that if I plug in the inverse into the original, that's the same as plugging the original into the inverse because they will both be equal to x. So to verify, you're going to do both compositions. So let's actually write that down. To verify, do both compositions. This is a proof, so show all your steps. Okay, you need to show me all your steps. You need to, every step you make actually has to be true mathematically, and we can't just make up math along the way to end up with x at the end. So I'm going to take, and it doesn't matter which one you start with, I'm just going to go ahead and take the original. So I have f, I'm going to make a home for my inverse. Everywhere there's an x, I'm going to take it out and put in this. So I'm going to putting in this notation here, and I'm going to put in the function here. But for now, it's a nice habit if you just take out the x, make a nice big set of parentheses to make a home to put in what you're going to put in. If you get into that habit, you're less likely to make mistakes along the way as far as what you're doing mathematically. All right, so in here is going to go f inverse x, because that's what I'm finding. And in here is going to go the cubed root of x plus 4. And now I just need to simplify all this. Okay, and I need to follow order of operations. I would say when people mess this up, this is the biggest mistake they make. So follow order of operations, aka PEMDAS. Okay, you can't just randomly cross things out. I see people going, oh, that's going to cancel out, and that's going to cancel out, and now I'm all good. You can't just randomly cross things out. You need to actually algebraically do this in order so that way I know that you know how you got there. All right, so a proof. If I do this first, which I would because it says exponents first, parentheses, there's nothing inside the parentheses I can simplify, but I can do exponents. So when I cube the cubed root, I end up with x plus 4 minus 4. And then add and subtract happens next. I'm going to take 4 minus 4, and I end up with x. Okay, so far this is correct. Now I need to go over here and do the inverse with the original function plugged in. So again, I'm just going to copy the whole thing down. I'm going to take the inverse. Wherever there's an x, I'm going to take out the x, put in parentheses. Then I'm going to go back through and put in my original function. So f inverse x of f of x. Put this part in, x cubed minus 4. And I'm going to show algebraically, step by step, not just by crossing off everything on the first step, what is happening. So, parentheses, nothing can happen inside these parentheses, but with a square root symbol, everything needs to happen inside of here. It's kind of an assumed parentheses. So we're going to do what's in here, which is x cubed minus 4 plus 4. So I end up with the cubed root of, inside the parentheses is x cubed plus 0. So just have x cubed. And now the cubed root of x is x. Okay, all of this together is what shows this proof. And this is mostly about being able to do algebraic manipulations correctly. All right, so I've left this problem for you to try. You have the original, you're going to find the inverse, you're going to find the domain and range of each, and then you want to graph them, make sure that they're flipped over y equals x, and then you also want to actually do the composition of both and see that they turn out to be x for both of them. If you're stuck at any point, just go back through your notes or rewatch the part of the video that will help you with this. All right, that is it. Thanks for watching. I'll see you in class.